right, let's take a look at the elliptic orbit problem one more time. In a previous video, I solved that by cheating by using the vis-viva equation for velocity. But how did we know that? That's the question. So let's try to prove this result again. That the energy, the orbital energy, is this constant, minus GMm over 2a, where 2a is actually the minimum distance from the center to the reduced mass particle, and the maximum distance when the reduced mass particle is here. So the reduced mass is circling here, orbiting around the total mass m plus m. And to be a little bit more efficient, let's change the notation to r1 for the minimum distance and r2 for the maximum distance. And here is this equation that we clearly can see here, 2a, where a is the semi-major axis. And let's take a look at the orbital energy here of the reduced mass particle. So here you have a kinetic energy, and here you have the gravitational potential energy for any distance r, wherever this particle is. And we can also easily show that the angular momentum for any r equal this mu r times the velocity in the phi direction. If you think about polar coordinates, you can divide it like if there is a speed here somewhere, you can divide it in one speed in the r direction, boom, and one speed in the orthogonal phi direction. But angular momentum and speed in the r direction is 0, so it's only the phi direction that can have any significance for angular momentum. And in polar coordinates, the real velocity squared can be divided up in the, as I said, the velocity squared in the r direction and in the phi direction. And because of this relation to the angular momentum, it can, the phi direction speed can be written like this. You can check it. So what will happen to the orbital energy then? Then you have one contribution here with the VR squared and the phi squared. We'll use this instead. So you then have this. It's an r-dependent term, and then you have the potential gravitational energy. And often we clump those terms into one and call it the effective potential, and it's only depending on r. So there is no velocity or anything in this one, because L is a constant, 2 is a constant, so it's just r dependent here. So then we have an expression that is a little bit simpler for the analysis of this problem. So then when you have the extreme points here, here's r2, look, and there is r1 distance. Can you see that right here the velocity is like this, purely in the phi direction? There is no velocity whatsoever in the r direction, neither here, not in that direction, only in the phi direction. So for the extreme points, we have that VR equals 0. And then the orbital energy further simplifies into just the effective potential for those points. That's what I'm writing here. And then we put in r equal r1 and then R equal R2. And since energy is conserved, energy is a constant, this must be fulfilled for this problem. This one must be equal to this one for the two extreme distances R1 and R2. So, and if you mathematically manipulate this equation, you will find that this will be like that. And then it's time to use equation 1, R1 plus R2 equal to 2A. Okay. I'm saying that here. So R2 equal this. Put it in here. And what do you get? Then you will get this term minus this term here. And after that, let's write down the orbital energy again. E equal this one here. But this term here equals this. So here's the energy. And when you put in these guys here, then you will see that that term and this term cancels perfectly. And what we are left with is only this guy here. And the reduced mass is m times capital M divided by the total mass. So those will cancel and you will only have minus GMm over 2A. And this is an exact result in classical mechanics. Okay, we are done. Thank you very much. See you later.